Hello, myself Kumar Reddy, and meet our talented team, the architects behind our Canny edge detection project, Urmil and Priyanka Joshi. Today, as we embark on focusing journey into the realm of computer vision, today our focus revolves around a powerful image processing technique that has revolutionized the way we perceive and analyze visual information. That is Canny edge detection. What is edge detection? In image processing, the ability to identify and extract meaningful features from visual data is important. Edges, the boundaries between objects or regions, play a crucial role in defining the structure of an image. The Canny edge detection algorithm excels accurately identifying real edges while filtering out the noise. Why Canny's method among the all methods? Out of all the ways to find edges, Canny's way is super good to find edges and fixing mistakes and staying strong. John Canny also wrote a paper about it called A Computational Approach to Edge Detection. So the project aims to uncover the algorithm's principle for real-world adaptability. In our project, we are not just talking about the Canny's method. We are also trying it out. This project takes a hands-on approach, constructing the Canny algorithm from foundational components. We are using the steps from the paper to see how Canny does its thing. We want to really get what makes it so special. Coming to the methodology, we have followed four main steps to achieve this goal. First step is preprocessing, second is gradient calculation, third is non-maximum separation, and last and final step is historical thresholding. Coming to the first step of our methodology, that is image preprocessing. And in image preprocessing, we followed mainly two steps, that is grayscale conversion and Gaussian blur. The first one is grayscale conversion. In simple terms, grayscale conversion is making colors simple. We start by changing the image to grayscale. Why? Well, it's like making things easier for the computer and our eyes. Imagine using only black, white, and shades of gray. That is called grayscale. Now, grayscale images simplify data processing by condensing color information into a single intensity channel and also reducing overall dimensionality in the pipeline. We use a special formula to do this. Following how our eyes see brightness in different colors. This simplifies the image, making it easier for our computer to understand. Second step is Gaussian blur. In simple terms, Gaussian blur is smoothing things out. Now let's talk about smoothing things out. It's like putting on glasses to see things more clearly. We use something called a Gaussian blur, which is like gently blurring the picture. This helps get rid of any weird spots or speckles that might distract our computer. We choose just the right amount of blur so that important details stay clear while the distracting stuff disappears. And these are the two steps we followed in pre-processing. And why do we bother with all of this? Okay? Grayscale and blur are like preparing a canvas before painting. We are getting our image ready for the real adventure. Finding edges with the Canny edge detection. Grayscale makes the image simpler and blur helps our computer focus on the important parts. Together, they set the stage for more accurate and reliable edge detection process. Now, I want my teammate to take over. Thank you.
Thank you, Vinod, for that introduction and explaining the first part of the Canny edge detection algorithm, which was pre-processing. Now, we'll talk about the second part of the edge detection algorithm, which is gradient calculation. First of all, what is gradients and what role do they play in the process of edge detection? So, gradients are like compasses telling you how quickly and in which direction the brightness landscape of an image changes. The way we are using doing gradient calculation in our algorithm is by using Sobel filter. A Sobel filter analyzes the surrounding brightness landscape and tells you how much and in which direction the intensity is changing. The following filters and weights were used to carry out gradient calculation. After this, we had these results. Now, as you can notice, the gradient calculation takes place in two different axes. The result on the gradient calculation on x-axis is on the left and on the y-axis is on the right. With this, the second part of the algorithm was complete. The third step was non-max suppression. Now, what is non-max suppression? Imagine a thick black line drawn on a white background. The Sobel filter would mark all the pixels along the line with a high gradient magnitudes, effectively creating a wide band of uh, wide band instead of a thin precise edge. This is where NMS comes in. It does the work in three steps. The first is iterative comparison. NMS iterates through each pixel identified as an edge. The second part is directional check. It compares the gradient magnitude of the current pixel with its immediate neighbors in the direction of the gradient. It uses 8 connectedness to find out the neighbors. Think of it as looking along the edge path. Third part is keeping the maximum. Only if the current pixel has the highest gradient magnitude among its neighbors in the direction of the gradient is it retained as a true edge point. All other pixels, even though they have high gradients, are suppressed and not considered the part of the final edge. This is very close to what we've studied in the course during thinning. With this, the second and third part of the algorithm are complete, and I will now hand over to Priyanka to explain the final part and the future scope of the project. Thank you.
As explained by Urmil about the non-max suppression, these are the final results we have achieved at the end of step 3, that was applying non-max suppression. Moving on to the next step, we'll understand how hysteresis thresholding is done. What hysteresis thresholding does, it actually identifies which edges are real and which are to be discarded, or what part of the edges is simply just noise or weak fluctuations. This is also done using a 3-step algorithm. The first part of it is defining, that is double thresholding, which is defining a high threshold and low threshold. Now, pixel exceeding the high thresholds are definitely classified as strong edges. So that is the first step. Next is conditional pass. Now, the pixel whose gradient magnitude lie between the low threshold and the high threshold enter a gray area. Now, there is a condition to decide as to whether they'll classify as a strong edge or not. Now, these pixels, if their gradient magnitudes and the ones which they are connected to have already crossed the high threshold, then they can be considered as a strong edge. That is, if a pixel provides a path towards a strong edge, it can be considered as a strong edge. This is the second step. And the third step is suppressing the weak. That is, for obvious reasons, all the pixels below the lower threshold will be not considered as edges, and they'll be just considered as noise or weak fluctuations. So this is the final process of our algorithm, that is hysteresis thresholding. Now, these are the results which you can see we have found out. On the left, you see our result. That is the results we have obtained using our customized approach for the Canny algorithm. And on the right, you can see all these functionalities have somehow been built using somehow been inbuilt in a function which gives the results which are present on the right. So as you can see, our algorithm has performed quite well, and it has detected a lot of edges. So the algorithm has performed well. Now, moving on to the how I would like to conclude and how our algorithm is important. Now, what we found out is that our custom implementation has successfully produced an edge map which fairly gives and captures significant changes in the intensity within the image. Also, as compared to the inbuilt function, the notable observation is a slight reduction in the level of detail in our custom implementation, which can be optimized using additional pre-processing, or adjusting the threshold values, or adjusting the filter parameters. This would be a future scope. Now, Canny edge detection algorithm is a very famous and important algorithm which has various applications and is currently being used for object detection and segmentation, motion analysis and tracking, feature extraction, and scene understanding, and most importantly, in medical imaging analysis. With that, I would like to conclude our presentation. I hope we've all understood the importance of canny edge detection and our custom implementation and the results it has given us. Thank you.